Sharon Glatzer. I'm the chair of this meeting, and I am really delighted to have Dr. Cherry Murray here to brief us on the Office of Science from the Department of Energy. Cherry is the newly confirmed since December director of the Office of Science, and as in that position, she oversees research in the areas of advanced scientific computing, basic energy sciences, biological and environmental sciences, fusion energy sciences, high energy physics, and nuclear physics. She has responsibility not only for supporting scientific research, but also for the development, construction, and operation of unique open access scientific user facilities. The Office of Science manages 10 of the department's 17 national laboratories. So it's kind of a good job. Prior to this confirmation, Cherry served as the Benjamin Pierce Professor of Technology and Public Policy. Oh, I have a microphone right here in my hands. Sorry, I totally forgot. And Professor of Physics at Harvard. Prior to that, of course, she served as the Dean of the School of Engineering and Applied Sciences at Harvard from 2009 to 2014. Prior to that, she served as the Principal Associate Director for Science and Technology at Livermore National Lab, and as Deputy Director for Science and Technology there from 2004 to 2007. Of course, Cherry has also held positions at Bell Labs and Lucent Technologies, formerly AT&T Bell Labs, where she began her career as a member of the technical staff within the Physical Research Laboratory and eventually finished her tenure there as Senior Vice President for Physical Sciences and Wireless Research. Of course, she's received numerous honors and awards. She's an elected member of the National Academy of Sciences, the National Academy of Engineering, the American Academy of Arts and Sciences. She was awarded the National Medal of Technology and Innovation by the White House in 2014 for her contributions to the advancement of sciences for telecommunications and the use of light for studying matter, and for leadership in the development of the STEM workforce in the United States. She's a previous president of the American Chemical Society. What did you say? You're kidding me! Of the American Physical Society and an APS fellow, and I also have to mention that she's a former recipient of the APS Maria Geppert-Mayer Award. So thank you very much, Cherry, for joining us this morning.
I am pleased to be here and really excited that this is the biggest March meeting on record. And it's approaching the 1999 meeting, which was March and April together. I think there are only 200 more people need to sign up, and it'll be bigger than any other APS meeting. So I am going to rush through these slides rather quickly so that we can actually have a discussion. And since I have a light shining in my face, I can't see you out there. So you may have to jump up and down if you want to ask a question. So the Department of Energy, as many of you know, is a mission-driven department. We have missions in national security. We have missions in energy, hence the name. But we also have a mission of science. So environmental cleanup is from the original Manhattan Project. The nuclear safety and security also arises from the Atomic Energy Commission. Science is an incredible, important part of all of these things, but science is a mission in itself.
Cherry, what if you stand on?
Good. So this Secretary of Energy, Secretary Ernie Moniz, decided to put science and energy together. So the Office of Science, front button. Aha, it's right here. Under the Undersecretary for Science and Energy, and all of the applied energy programs, except for ARPA-E, which reports directly to the secretary, are under the Undersecretary for Science and Energy. Every now and then, science and energy get put together in the department, or taken apart, or put back together again. They're now together. And it's become more and more critical to have science connected to energy. And you'll see part of that. The National Nuclear Security Administration, otherwise known as NNSA, is about 40% of the budget of the department. Science and energy are also about 40% of the budget. And the rest of the department is about 20%, obviously, but that mostly is environmental cleanup. And we are always working on 3 budget cycles at the same time. The Omnibus Appropriations Act actually was passed last year, and both the House and the Senate are madly writing bills as we speak. It'll be interesting to see whether we go through a continuing resolution this year or they actually get the bills written. But the appropriators are writing at this very moment. And we have just finished testifying on our budget proposal for FY17, and we're starting to think about FY18. If you look at the FY17 proposed budget for the Department of Energy, first off, you will notice a number of things. We see here FY15, 16, and proposed 17. What I said, 40%, 40%, 20%, and everything else, other, is the administration of the department. Also, the department runs power marketing administrations. They run the national, the federal dams who actually sell power. The nuclear security part of the department had a big increase last year and a smaller one this year. EM stays just about the same, environmental management. And you'll see this enormous jump in science and energy, which is known in the administration as mission innovation for clean energy technology. In the COP21 conference, 20 nations got together actually on the stage and proposed that they would double the clean energy technology innovation R&D budget by a factor of 2 in 5 years. And so this is a proposal by the administration to really jump up both science and energy. So science would increase by 6%, and energy would increase by something like 20%. Thanks. Do you want me to use that instead?
It might be brighter.
Okay. Let's see. Yep, okay. Whoa. That might be a little too bright. The other thing I want to point out in the budget, though, I'll use this one, is this interesting piece, mostly here, but some here, and a tiny sliver in science called mandatory. So this is a statement that the appropriations budget caps, which had been agreed to, are too small. And this here is the 21st Century Clean Transportation Plan investments, which would be taken out of a tax on oil revenues. So I expect that is not going to happen. So if you just look at these numbers right here, that's the proposal in appropriations, which is pretty astounding. So as I said, the department is a mission-driven agency. we are up here at high risk basic science research to maybe getting to feasibility. The department does everything to help large companies deploy with loan guarantees. This is not in the department, that's venture capital. ARPA-E kind of goes from science to getting good prototypes and maybe launching businesses. And the applied technology offices work both with a little bit of science, but mostly deployment and engineering to lower costs. And costs have lowered dramatically in the last 10 years. For example, the cost of LEDs has gone down by 90%, 90. They are now 10% of the cost that they were 10 years ago. And the idea of mission innovation is not we're going to turn off the lights, but we're going to make the lights so much more efficient and so much more lower cost that everybody is going to use them. We also have a number of modalities that we fund, and I know this is confusing, so this is a tutorial for you. You can't see this, but this says core research, individual PIs. That's mostly what the Office of Science funds. But since 2009, we fund what are called energy frontier research centers. These are about $2 to $4 million a year for over 5 years. It's going to move to 4 years, so we can go on a 4-year, 2-year cycle, offsetting them. And these have been extremely popular. These are somewhat more focused on use-inspired research, although some of them are also call them discovery research. We also fund bioenergy research centers and hubs. These are $25 million a year, so very large entities focused on, obviously, bioenergy. One of them is focused on storage. One hub is focused on storage, and one hub is focused on fuels from sunlight. And the bioenergy research centers are ending next year a 10-year cycle, have really influenced biofuel production in the U.S. They're now actually plants for biofuel production, where there was nothing 10 years ago. And then there are these consortia and crosscuts, which is a new development since this secretary. What that is a coordinated program coordinated across the department focus on something important, all the way from science through even loan programs, but certainly through the applied programs. And we are also in a number of these crosscuts. The crosscut that has been most effective, that started, I'd say, 5 years ago, is the grid crosscut. The grid around the world is transforming in a way very similar to how the internet transformed. And it is really happening fast. And it's pretty exciting. We also have crosscuts in subterranean science, because it turns out that is important for all aspects of energy. Everything from extracting resources to putting them back in, as in carbon sequestration, and geothermal. All right, I will quicken my pace. We are the largest supporter of physical sciences in the US. We actually fund 90% of the nuclear physics, about 70% of the high energy physics, and probably around 50% of the condensed matter physics, but we also fund chemistry, geoscience, some biology as relevant to energy, and 30% of the computer science and math, and that's growing. Of our budget, which in FY16 was about $5.4 billion. 42% of it goes directly to research, and it is probably not well known, but 40% of that 42% goes directly to universities. And we fund over 300 institutions and 20,000 scientists, although I think it's really considerably larger than that. We also spend a lot on construction, almost $1 billion per year, and facility operations are the rest of the budget. We have it's now about 34,000 scientific user. And I'll talk a little bit more about that. So here are the programs. Computing, which is applied math and computation. Basic energy sciences, which is kind of condensed matter. And it also includes chemistry, material science, geoscience. Biological and environmental research, which I'll talk about later. High energy physics, nuclear physics, and fusion. And we operate, many of you I recognize in the audience, and many of you are on our advisory committees. So we have federal advisory committees, otherwise known as FACA committees, the Federal Advisory Committee Act, and they help us, along with the scientific community, in planning our programs. So there are probably just around 50 of these basic research needs workshops that have happened over the years, which is looking at what are the new developments that we should be funding, basically. In basic energy sciences, since this is mostly a condensed matter crowd, I will talk about that a little bit more. It's called basic energy sciences because this is the basic science underlying energy technologies. We have challenges in the basic science. This is a recently come out 2015 overlook of what is cool and new in, for example, hierarchical architectures, definitely imaging across multiple scales, understanding non-equilibrium matter, coherence, both in light and matter, and looking at what you can find on the department's website, the Quadrennial Technology Review, and all of its 1,000 pages of what is happening in energy technologies today. And that was done with the science and energy programs and was published last year. So in basic energy sciences, you can see the huge focus on facility operations, and most of the big user facilities are in BES. It's also almost $2 billion. All the X-rays, neutron sources, and nanoscience research centers are located in BES. And all of them wish to have upgrades. And it's important, actually. It's incredibly important to be world-leading, and these are all world-leading sources and centers, and they must continue to be world-leading. The issue is, of course, in what priority order do you actually do these upgrades? Because each upgrade is relatively expensive. So I'll talk about that a little bit. And of course, we fund a lot of research in material science, chemistry, and geoscience. The Energy Frontier Research Centers and the hubs are in BES. And in 2016, there are 5 new Energy Frontier Research Centers that are being the opportunity is out on the street, I believe, as of next week. And in FY17, there will be 5 others in subsurface imaging. In high energy physics, the P5 panel report, which was in May 2014, really set the strategy for the field, and they are very, and we are very proud that 3 Nobel Prizes very recently have been won in these particular areas, and we're focusing on neutrino mass, and hopefully we'll get some Nobel Prize there. The importance of having the entire community, and this is the international community, come together and create a strategic plan is, I will say, tantamount. That makes it very, very easy to actually propose a budget and get it through, because it looks like we know what we're doing. So we're focusing on construction, facility operations, and research. The majority of the, call it boson research, is going on in Europe at CERN, and we are a very large part of that. We are the largest partner, actually, in CERN, and the 2 detectors, Atlas and CMS, are also proposing a high-intensity, high-luminosity upgrades, and we will be part of that, as well as upgrading the CERN linear accelerator. At the very same time, the field wants to build a very large neutrino study, and that's an issue to actually fit it in the budget. Very important experiments. There are some smaller experiments as well, searching for dark matter and other exciting things, and muons, and looking at whether muons can go to electrons, and very cool stuff. Fitting it in the budget is always a interesting dance, let me just say. We fund computer science and math, but the slight difference in the Department of Energy is that we also fund collaborations across fields in computational science. And so what the fields need in these are requirements documents for, this is exactly the kind of big iron and software architectures that are needed to push the fields. And Sharon is on the ASCAC advisory committee. The big thing in the Department of Science now is Exascale. I'll talk about that a little bit later. Moving to Exascale, you can see that we don't build stuff, we lease it, because we collaborate with industry as they are building the computers. That's why you don't see a lot of money being spent on that. Money goes into leases right here. We have high-performance leadership computing facilities. These are also user facilities, and I'll talk a little bit about that also later. Nuclear physics was a little bit disorganized, I would say, about 5-10 years ago, but since then have really gotten organized and have a strategic plan which is compelling. And this has changed the picture dramatically for nuclear physics. And we are right now building, well, we're not building this, we're building EFRIB, which is the facility for rare isotope beams. The next proposed cool thing to do is a electron-ion collider. We're starting a National Academy study to do the science-based for such a machine. And when EFRIB is finished constructing, we expect to, and that's in 2022 or so. We expect to ramp up with possibly this. And so nuclear physics, this is FRIB construction for the most part. We just finished CBAF upgrade at Jefferson Lab. Atlas is at Argonne. Rick is at Brookhaven. And we have in our budget proposal 24 weeks of RIC operations, which is extremely good. It's as much as they can do because they're taking it down to do a few upgrades. Their RIC has been getting higher and higher luminosity and very, very cool results, and is not, I will say this, not likely to be shut down. Rumors of shutdown are untoward. It's just doing too much good physics. Okay, for the biological and environmental research, otherwise known as BER, there are a bunch of National Academy studies, White House studies, both of these, and of course BRAC studies. We do the biology that's relevant for energy and environment. So a big push on microbiome. This is not your microbiome. That's NIH. We are the microbiome of everybody else. So the Earth's microbiome, all of the microbes in the oceans that are relevant for oxygen production and atmospheric, also the carbon cycle is incredibly important. The user facilities are a Joint Genome Institute. They are doing genomics of everything but humans, I would say. So, for example, recently eucalyptus genome was whatever you do with genomes. It's not discovered. Sequenced, yes. Which is actually important for energy crops. And also seagrass, which interestingly was a plant on land, then moved to freshwater, then moved to saltwater. And understanding how plants can, what are the genes that allow plants to actually thrive in saltwater is becoming more and more important. Let's see, what else? Oh, yes. ARM is, there are two facilities, but there are also a bunch of chemistry and atmospheric chemistry equipment that you can check out. You write a proposal, you can check it out, and then you can go do measurements. So there are folks right now up in the Arctic looking at what emissions from permafrost, a rather important thing that we need to understand a lot more about. I will point out a ARM measurement from Harvard, which was looking at pristine emissions from trees in the Amazon. It's called the Go Amazon Project. And how does that change as you move out to where it's very close to farmland? Things that we need to understand about the atmosphere. And EMSL is a chemistry and focus on environment user facility at Pacific Northwest National Lab. The fusion community has been having a bunch of workshops focused on what kind of new things are very, very important as we're looking to study burning plasmas. And this has come very, very well over the last year. They are focused on, there are two US machines, a lot of international collaborations, and I will talk more about ITER in our issues section of the paper. And also they fund plasma science and also materials in extreme conditions that would be relevant for doing mostly magnetic confinement fusion. We steward 10 national labs of the 17 national labs system. Those are the national labs. I will just flash this picture. But we only fund 60% of those national labs. The national labs actually fit in between university research and industry. And they do multidisciplinary things, and they really work as a network. And to show you the complexity of this network, I will show you the funding profile from the programs. You are now familiar with all the acronyms of DOE. This is science. These are the applied energy programs. That's NNSA, nuclear, and this is waste cleanup. But you can see there's somewhat of a complex nature to the funding. The funding that science does, and more of the energy programs, is competitive. So whoever wins the competition gets funded. And you can see that almost every lab is getting funded by almost every program. They really do act as a network. We have 28 user facilities, soon to be 29 when FRIB comes on board. And they are big, and they are expensive, and they are free to the users, competitively. This is another $2 billion of operations that is free to the users. 60% of the users, 65% of the users are from universities. So think of it as another $1 billion going, or $1.2 billion going to your grants. If you look at the mostly light sources, these are the basic energy science user facilities. You can see the user community growing dramatically. And what happens when you shut down for an upgrade? This is NTS. This is NSLS at Brookhaven, shut down this year for an upgrade. It's now up again. But these are the light sources. And these are all the nano centers and neutron facilities. If you look at all of them, including the big hardware machines in the computational user facilities, we have about 34,000 total users in FY14, 65% from universities, and 23% from DOE labs. This other includes other national labs, international people, and federal agencies. So NIH makes good use of the light sources, for example, to do all of the protein crystallography in the US. I want to point out on our website is a nice interactive tool that lets you see the grants that go out, called federal assistance, to universities and some to industry, but mostly we fund universities, and also where the users come from. The users come from all 50 states and Puerto Rico and Washington, D.C., and of course international as well. So now the issues. All right, you saw that we actually spend a great deal of time, effort on world-leading free science user communities for the community. How do we balance research funding versus building these, making sure that they are world-class? And then you can see the others. I'll go through them one by one. So here's the issue. First of all, I'll point out this was the stimulus package. We were ready to go with the stimulus package and put that into construction. So that helped tremendously. That was actually NSLS. here's the issue. So 50% of the research back in 96 was 50% of the budget was research. And now it's down to 42%, and the facility operations and construction are getting higher. And that is because the facilities are getting more sophisticated, there are more of them, they need to be world-class, and each of them is getting upgraded. Many of them are getting shut down because they're no longer world-class. This is always a difficulty for the community, but it's the right thing to do. But it's rather tricky. I will just show you the funding profile for BES construction. And you can see that that was the spallation neutron source being constructed. That took the entire budget of construction. Then other things came on, and they have to be slotted in. And so we need to have a prioritization of when we do the new construction, when we do the upgrades. This is always a delicate balance because every community, of course, wants their upgrade. And I will say every congressional district wants their upgrade. Okay, we also want, one of my goals of, and one of the reasons I agreed to do this job for the next year is, as I said, there is incredible revolution in energy technologies taking place right now, and it's needed for the Earth. And I want to make sure that we continue to do discovery research as well as support the energy technology innovation because it needs a transformation and you need science in order to really get transformational changes. So, looking at what is scored by the Office of Management and Budget as mission innovation in the department, this is the first year that this scoring was done. And so we went back and looked at what was it right now in the FY16, taking the same scoring and moving backwards to see, so what's changed. The mission innovation part, the use-inspired part of Office of Science has increased slightly, but it's around a third of what we do. And that's, I believe, perfectly reasonable and needed. It's about 70% of what the applied energy programs do. And so the balance, I think, is quite good. Some of the applied energy, some of the stuff that's not scored, you would say, why aren't the applied energy programs all scoring 100% mission innovation? And it's because, for example, nuclear waste storage, the waste from nuclear commercial power plants, is part of nuclear energy budget, and that is not scored as mission innovation, despite the fact that if you do not have a place to store the waste, you can't build nuclear power plants. But that's just the way OMB decided to do it, and that's why it's not 100%. Also, there is research going on in more efficient fracking, let's just say, in fossil energy, and that's not scored. What is scored mission innovation is carbon sequestration and clean coal technologies. Okay, for science, we got an increase, but we also got another from OMB pass back of you got another $100 million to spend on mission innovation. Tell us what you want to do. So we had a major scramble at the end of the year, and this is what we came up with, and it passed muster, so it's in the president's budget. So we're going to do computational partnerships with EFRCs. Some of the 32 current EFRCs have really done spectacular stuff and actually need a little bit more computation. And so this will be a SciDAC partnership with the EFRC crowd. I thought that was a great idea. New catalysis, looking at enzymes, because you know what? Nature does things really, really well, maybe not very efficiently, but it does it very low energy. And so can we learn from nature and create enzymes, for example, in ammonia synthesis, which is the molecule that's most synthesized for fertilizers and uses something like 7% of the world's energy supplies. Can we do something better? Materials for clean energy, this is like self-healing materials are now becoming very, very exciting. It isn't now just two types of epoxy cylinders inside of a material that when you squish it, the cylinders open in the epoxy. That was the old self-healing materials. This is now materials that truly heal themselves. Let's see, what else? Chemistry under harsh or extreme environments, otherwise known as batteries or fusion environments. Biosystems design, so the bioenergy research centers, which, as I said before, are $25 million per year. There are 3 of them, so $75 million per year, are coming to the end of their lifetime of 10 years. They will be shut down in FY17, and a new, what's called FOA, funding opportunity announcement for new, this is now biosystems design centers, will stir the interest of the community. That's the bioenergy research centers. And a big focus on microbial environmental things. Whole device fusion modeling, which is really an exascale problem. Okay, exascale, speaking of exascale, a gazillion studies have been done on exascale. It's hard. We are actually, maybe 30 years ago, we were saying we're coming to the end of Moore's Law. Now we really are coming to the end of Moore's Law. And the reason we are doing that is we're getting down to atomic scale, and the devices are putting out too much energy. So we need to have very low energy hardware. The software environment is becoming parallel because you just cannot, you have to go massively, like million processor parallel. It's tough. This is a cross-cut across the department with the NNSA, the nuclear folks, who pushed the scale of computing by about 12 orders of magnitude over the last 15 years. And we want another 1,000, just 3 orders of magnitude. It's becoming even harder, and it's co-design, software and hardware, and it's design with industry. We have memorandums of agreement with industry. We need to actually understand how you're going to make the chips now. This is not riding on Moore's law anymore. And then we will, it's not business as usual. The other thing we're looking at is beyond exascale, von Neumann type architectures. For example, maybe neuromorphic architectures. Definitely machine learning, deep machine learning, and big data. So scientific big data is just going bananas. And we need to be able to understand it and handle it much better. For example, DOE is building the detector and the data system for the Large Synoptic Survey Telescope. That is funded by NSF. So we're building the detector and the data system that's going to handle something like a petabyte per day. And so you obviously are not going to store that. You have to do something quickly and understand interesting objects quickly. Okay, so now other issues, international partnerships and big science. And actually, this is not an international partnership, but it's international competitiveness. These are international partnerships. So the defining moment in fusion energy sciences is happening this year. This happened to be on my watch. Here it is. So ITER, which is funded by the 7 partners, mostly by the European Union, which funds about 40% of it, being built, that's what it looks like at this moment, in Cadarache, has been an agreement for 10 years. 10 years ago, when we signed the agreement to be one of the partners, along with India, Russia, China, Japan, Korea, it was going to be about $1 billion US money that we put into our own industry to build things, to put into the very large tokamak. That's a person. Now it looks like it's more like $4.5 to $6 billion, and the time for first plasma has been pushed out considerably into the middle of the next decade. And Congress is hopping mad. I'll just put it that way. So you can read the Secretary of Energy, not later than May 2nd, and they keep asking him, what's your answer? What's your answer? Because we're writing the bills right now. Shall submit to the Committees on Appropriations of both houses a report recommending either the U.S. remain a partner in the ITER project or terminate participation. So this is a defining moment. There are issues either way. If we continue, this, the community believes, is the fastest way to get to burning plasma. If we continue, how does it fit in the budget is a very good question. If we stop, how are we as an international partner is a very good question. And it's an extremely good question because of the next project, which is our own international project, which is a neutrino observatory. You remember Dusel? Dusel has now turned into Dune here. That's right. Very large underground particle detectors, argon detectors, will be put to look at neutrino oscillations as they will be produced at Fermilab and shot to South Dakota. You don't have to dig a tunnel for neutrinos. These are going to be built by CERN. So this is the first time CERN has actually produced something for an international project that's not at CERN. And it's incredibly important that we are a good international partner. And we're going to build the rest of it, and it's going to be horrendously expensive. It's horrendously expensive. It's about something like $250 million just to excavate these things. It is a gold mine, but there's not very much gold in there, I'm told. And we're not allowed to keep the rocks. But that is a very, very exciting new project that needs to be fit into the budget, and the international agreements need to be cemented. There's an agreement we will work together. There's not an agreement of we will create this for you. And last, the first thing I signed as I took office on December 21st this year was a charge to the Basic Energy Sciences Advisory Committee prioritizing the proposed upgrades for 5 different of the user facilities. It is highly likely we will do all of these upgrades, and they will be done in order. Question is, what priority order? And so we're asking the usual question about facilities, which is, World-leading science, absolutely number one. Will these upgrades lead to world-leading science? And number two, is the team that's proposing it ready to construct? Because it could be great world-leading science, but they're not ready yet. They haven't done all the engineering R&D, in which case we'll fund that and then upgrade later. What happened in 2013, looking at one new facility and 2 proposed upgrades, Basic Energy Sciences Advisory Committee subcommittee basically said those upgrades are not world-leading. They will, by the time they get constructed, they will not be world-leading. You need to go back. And so my predecessor, Bill Brinkman, handed the report back to the folks and said, we need world-leading instruments. So out of that come 2 of the proposed upgrades, one to LCLS, the free electron laser, which, as it's starting its construction right now, is already proposing the next upgrade. And one source was, the money was found to do new stuff at APS upgrade in argon, advanced photon source, and also LCLS from killing the other proposed project. So we have a budget which luckily has been increasing and is doing well, but it's finite. So the community needs to understand that we can't do everything at once. We need to roll them out somewhat. And that is the end of my talk, hopefully. Thank you. Yes, yeah. I was hoping that we'd have time.
What about the inertial confinement? Because this research on fusion has been going on for the last 60 years without any results.
And it's always 50 years away. Yeah, the inertial confinement fusion is actually funded by the NNSA. And as you're probably well aware, the National Ignition Facility at Livermore, which is about $500 million a year operating funds, is working on inertial confinement. So with our meager funding in the Office of Science, we are focusing on magnetic confinement. And I thought you might ask, well, what about all these other new cool ideas, stellarators, and there are something like 50 startups in fusion energy, which is very cool. It may be, we may be, as I said, it's a defining moment for fusion. We may be getting out of the old ways of thinking about things and doing something totally different. It is a defining moment because as we get to actually considering what you would actually need for a power plant, it's an international experiment. It cannot be managed the way ITER is. CERN has a very good model for managing things, and the ITER model is incredibly cumbersome. Yes.
My question is also about fusion. I was kind of surprised that you put ITER in comparison with Joule, whereas it should be compared to other energy fountains.
Well, yeah, but
So it seems it's not the right strategy.
I just got exactly the same question from a lead staffer on the House Science Committee. So why isn't fusion energy in applied energy and not in science? What happened was it was in energy in 2009, something like that, 2007 maybe. TFTR, the tokamak fusion test reactor at Princeton, was shut down. And when that happened, it got moved to the, it was no longer called fusion energy. It was called Fusion Energy Sciences. It got moved into the Office of Science. So we're supposed to be looking at the basic physics, and it's mostly physics, but also chemistry and material science. That if we get, let's just say 25 years from now, because it is 50 years out, 25 years from now, if we have a concept that looks like it could actually produce a reactor, then yes, it needs to move to the applied energy programs. We probably would still need to have some kind of, call it basic plasma science in the Office of Science. But you're right.
I have a practical question. If the electricity went out, the lights went out, we'd all be in the dark. How efficient is the electrical grid? Does the DOE manage it?
No.
And
how efficient is it?
And is it international?
If you,
how much energy is lost in transmitting?
Oh, let's see. No, it's worse than that. First of all, there are 17,000 operators of the U.S. grid. There are 3 pieces of it that are in synchrony. Each piece is in synchrony. The northeast piece is the one that went down most recently. It is connected into Quebec, so it is somewhat international. We are not connected to Mexico, but that might happen. There are discussions right now, 3-party discussions. Should we have a North American grid? It's called the North American grid, and it's U.S. and Canada. It is really complicated. Probably like the internet, that's a good thing, because everyone was claiming that the internet is going to crash and burn, but it doesn't, because it has you can interoperate with the internet. There are different providers. It is asynchronous. The grid is going to have to be made up of microgrids that can just contain themselves, if they have a problem. The transmission loss is extremely high, so you actually want to have local energy production. This is good for solar. It's not so good for wind. It's good for solar. Even in Germany, it has a huge amount of, so that's North Europe. The loss going from whatever source of energy you have to electricity is also extremely high. We lose about 70% going from, let's just say, coal to electricity. Then the transmission loss is about 50%. So if you go to the DOE website and look at the energy Sankey diagram, you can see there's these enormous losses in the system. If we could use that, either waste heat or make things more efficient, we don't have to use more energy. We just save it. And so that's another part of mission innovation. It's really high tech. So, for example, instead of, way back in the 1890s, there was a big fight between AC and DC power transmission. AC won, and that was Westinghouse, actually. Edison lost. He wanted to do DC power transmission. AC won because transformers work. Well, we can do things with power electronics now. We don't need to have transformers. Transformers are actually kind of lossy. And it is actually, you lose less by having high voltage DC lines, possibly superconducting, than you would in high voltage AC lines. So the 3 parts of the grid, they're the northeast section, the western section, and Texas. Believe it or not, they are connected by DC lines. So if you're thinking, well, you have all this wind in the middle of the country, and why don't you just, put it through some kind of transmission line to the end of the northeast corridor, which is where most of the people live. The problem with that is you lose too much unless you do something cool like superconducting, big pipes. But then we don't even like to build pipelines in this country. So try to build a transmission line across the country. Mm-hmm.
Who's responsible for the grid? Who manages it?
Grid operators manage it. So there are something like 160 grid operators. They are coordinated through the Department of Energy Grid Consortium, so they're actually talking to each other. NIST provides the standards for the grid so that you can interoperate. It's very complicated. The regulation of the grid is by the states, so there are 50 different regulations. And the interstate transmission of energy is regulated by DOE. So it's just mind-boggling.
Here, back there,
What factors will come into play to decide whether the US remains a partner? What factors?
Oh yeah, we're right now doing 2 reviews of the project. One is a serious project review, and the other is a management review. The management review, as you're probably well aware, there's a new Director General. The management review happens every 2 years. It's just the normal management review. But those will be incredibly important for informing us.
You mentioned several times the $2 billion investment in these greenhouse gas.
Yes.
And you also mentioned the 67 benefit that the universities are getting. While that's wonderful, I come from the University of Virginia, individual investigator. I think an issue here is the funding of the individual investigators. The NSF budget, for example, particularly for materials research, has remained static for the last 20 years. And it was a bullet item, the first bullet item, the challenge that you had, a balanced challenge. But I think the 1.2 billion is great. It needs to be supplemented at least by that much funding individually.
Yeah, well, we do, and that is one of my priorities, to make sure that we do not lose the individual investigators, because you need this, I'll call it 1,000 flowers blooming, as a base. Then you can start thinking about doing what are the energy frontier research centers, but you can't lose that base. That's incredibly important. That is why we are pushing out the facility construction to longer than people want, because we have to keep that research base. And yeah, you can apply to basic energy sciences and material science, we also have, for universities, slightly larger grants than NSF does, because we believe it's important to, let's just say, have 2 graduate students and not just 1 graduate student funded. We also, I forgot to mention, this is not in material science, but in nuclear physics, we fund what are called centers of excellence at universities. I know MIT has one, which funds theory groups. And, MIT's funding is $5 million a year or something like that. And it's been that way for 30 years. So it is very stable funding, unless you really become uncompetitive. They do get competed every now and then. But yes, I hear you, and so do the program managers, and their focus, even on the mission innovation stuff, we wanted to have individual PIs with good ideas.
Yes. Do you think it's possible in the next 30 years that the big supercollider project starting to come to fruition?
It'll probably be the ILC, International Linear Collider. Japan is thinking about, for the last 10 years, hosting it. So there would be the ILC in Japan, the neutrino experiments in the US, and the LHC in Europe, and that would be a good balance. Japan is not having a great financial situation at this moment, so they're still thinking about whether they want to host it.
Any other questions in the back?
As far as conceptual design for this next generation fusion experiment, are there any technical additions that are proposed?
Oh yeah, there are quite a few.
Is there a conceptual reactor design proposed higher?
No. In fact, well, there is a, ITER is a science experiment. It's supposed to get to burning plasma, but it is not a demonstration reactor because there's a lot to be learned in terms of confinement, in terms of walls, and can you breed the tritium that you'll need, and all sorts of stuff. That's what ITER is supposed to look at. After ITER, it was supposed to be something called DEMO, which is a demonstration reactor, which is not really designed yet. There also probably needs to be a plasma material study, which is separate from ITER and separate from DEMO. And there are no, it's in a European roadmap that they will go to DEMO. I'll say that.
Last question.
So you mentioned Japan and finances. How about China? Is there any discussion about incorporating China into some big international project?
Yes, the ITER has China as a member. China is building synchrotrons, is building NIF-like facilities, big lasers, and is actually looking at our roadmaps and following them to actually build up the science infrastructure. We are collaborating with Daya Bay in a neutrino experiment with China. There is a very, very big energy collaboration with China, with DOE, and we have a memorandum, an agreement with the Chinese Academy of Sciences to do science. So yes. Are they proposing to do the next big accelerator? No. Actually, they don't have the expertise that the Japanese do. Will they have it in 20 years? Probably, because they're really building up their science infrastructure. And they'll, I will imagine some high-energy physics is going to be done. It has to be international. As I said, fusion has to be international. Nuclear physics is getting to the point where it's going to need to be international. And so we need to use all nations, expertise. All right.